Okay, thank you very much, Neeraj. I hope that I am audible to you, all of you. Okay, so let me, yes, share my screen. Yes, okay. So, my dear friends, till now we have completed the topics of the civil engineering, which have been allotted to me in the area of the fluid mechanics and machinery. Now, somewhere we have discontinued the mechanical engineering classes, but now again we are going to resume with the mechanical engineering. And before your examination of the gate, we will finish up this topic of the mechanical engineering. I hope that all of you are studying well, all of you are preparing well for the examination because mechanical engineering paper of the gate examination, it is scheduled on 13th of Feb. So only 15 days, 17 days of time is remaining with you to brush up the knowledge, to take it to the next level, and try to do the practice of the numericals involved in each and every topic. So now the today's lecture is being arranged on the theories of failure. So we will see what is meant by the theories of failure and then its significance, its utility in the subject of machine design. So already the subject of machine design we have started. In that subject we have covered basically the brake design, clutch design and the gear design, and few more topics are remaining, and that few more topics in this machine design is the theories of failure, fatigue strength and the ascent diagram. So theories of failure, the material properties are usually determined by simple tension or the compression test. All of you are aware that the tests are conducted. The tests are called as the compression test and the tensile test. And these tests are conducted to check the properties of the material, tensile properties and the compression properties of the material. Whenever any new material is also being developed, for example, we nowadays we are talking about the nano material which is developed, okay, nano fans, nano material which is to be used in the various cases, various manufacturing also, various design component also. For example, the people are trying to use the nano materials even in case of the manufacturing process, even in case of the 3D printing and the additive manufacturing. So whenever the material properties, it is to be determined by the compressible compression or the compression stress. In this case, the mechanical members are subjected to the biaxial or the triaxial stresses. Okay, because when you conduct a test, what will happen? These mechanical members are subjected to the biaxial or triaxial stresses. To determine whether a component will fail or not, some failure theories are proposed which are related to the properties of the materials obtained from the uniaxial tension or compression test, which means that we need to check in the beginning whether that material will fail or not. So some of the failure theories which are being proposed are related to the properties of the material obtained and from uniaxial tension or the compression test. So initially, we will consider the failure of mechanical member subjected to the biaxial stresses. The theories of failure which are applicable for this situation are that is maximum principal or normal stress theory, which is called as the Rankine theory, then maximum shear stress theory, which is called as the Guest or the Tresca theory, then maximum distortion theory, that is von Mises and Henke's theory, then maximum strain energy theory, that is maximum principal strain theory. So these are the theories of failure which are applicable for this situation. So ductile material, you know that there are properties of the material like ductility and the or the ductile material and the brittle material. Okay, and you are already aware about the definitions of the ductility or the ductile material and the brittle material. So ductile material they usually fail by yielding, and hence that limiting strength is the yield strength of the material as determined from the simple tension test, which is assumed the same in the compression ratio, which means that the ductile materials usually fail by yielding and their limiting strength is nothing but the yield strength of the material, which can be calculated by the simple tension test and which is assumed to be the same in the compression also. For brittle material, the limiting strength of the material is the ultimate tensile strength in tension or compression, which means that the difference in the ductile material and the brittle material. In case of ductile material, the yield strength will be the limiting strength of the material, and in case of the brittle material, the ultimate tensile strength in tension, okay, or the compression is the limiting value. Then maximum principle or the normal stress theory, that is Rankine's theory. It is assumed that the failure or yield occurs at a point in a member when the maximum principal or normal stress in the biaxial stress system reaches the limiting strength of the material in a simple tension test. So in this case, maximum principal stress is calculated in a biaxial stress case and is equated to the limiting strength of the material. So maximum principal stress, that is sigma 1 is equal to sigma x plus sigma y divided by 2 plus square root of sigma x minus sigma y divided by 2 whole square into tau square xy. So look at this figure, the rectangular cross section is being shown. This is the sigma x and tau xy in the y direction, the sigma y. So minimum principal stress is equal to, that is this is the maximum principal stress. So maximum principal stress, that is sigma x plus sigma y divided by 2 plus square root of sigma x minus sigma y divided by 2 whole square plus tau square xy. So minimum principal stress is nothing but the sigma 2 is equal to sigma x plus sigma y divided by 2 minus square root of sigma x minus sigma y divided by 2 whole square plus tau square xy. So for ductile material, the sigma 1 should not exceed SYT by FOS in tension. So FOS is the factor of safety for brittle material. So sigma 1 should not exceed SUT by FOS in tension. So this theory is basically applicable for brittle material which are relatively stronger in shear and not applicable to ductile materials which are relatively weak in the shear. So then boundary for maximum normal stress theory under biaxial stresses. You can see here the SYSC, SYT, SYT, SYC, sigma 2, sigma 1, sigma 2 minus sigma 1. The maximum shear stress theory, that is GAST or the Tresca's theory, the failure or yielding is assumed to take place at the point in a member where the maximum shear stress in a biaxial stress system reaches a value equal to shear strength of the material obtained from simple tension test. So the failure or yielding is assumed to take a place at a point where the member, the maximum shear stress in a biaxial stress system reaches a value which is equal to the shear strength of the material obtained from the simple tension test. In a biaxial stress case, the maximum shear stress developed is being given by tau max is equal to in bracket sigma x minus sigma y divided by 2 to the whole square plus tau square xy. Here, tau max is equal to T divided by factor of safety FOS. So, where tau max is equal to SYT divided by 2 times of FOS. So, this theory is mostly used for the ductile material. Yes, maximum shear stress theory or the Guest or the Tresca theory is used for the ductile material. So here Morse circle for uniaxial tension. You can see here the Morse circle for biaxial condition, sigma 2 0 sigma 3 sigma 1. This is tau max. Then no failure within these boundaries. Uniaxial tension. This is plus tau SYT plus. So sigma 1 minus sigma 2 divided by 2 is equal to tau max SY divided by 2. According to the maximum shear stress theory, tau max is equal to SYT divided by 2, and also tau max is equal to maximum direct stress minus minimum direct stress divided by 2. So assuming that sigma 1 is greater than sigma 2 is greater than sigma 1, sigma 3 is greater than sigma 2, and sigma 3 is equal to 0. So the case 1, that is first quadrant, sigma 1 and sigma 2 are positive. So tau max is equal to sigma 1 minus sigma 3 divided by 2. So sigma 1 plus 0 divided by 2 is equal to sigma 1 divided by 2 is equal to SYT divided by 2. That is sigma 1 is equal to SYT. Case 4, fourth quadrant, sigma 1 is positive and sigma 2 is negative. Then tau max is equal to sigma 1 minus of sigma 2 divided by 2 is equal to sigma 1 sigma 2 divided by 2 is equal to 2 sigma divided by 2. Then tau max is equal to sigma is equal to SYT divided by 2. So second quadrant, that is sigma 1 is negative and sigma 2 is positive, then the tau max is equal to sigma 2 in bracket minus of sigma 1 divided by 2. So finally it comes out to be sigma 2 plus sigma 1 divided by 2. So 2 sigma 1 divided by 2, and then tau max is equal to sigma 1 is equal to SYT by 2. So the case 3, which is in the third quadrant, where the sigma 1 is the negative and sigma 2 is more negative. Here the sigma 1 and sigma 2. Then tau max is equal to sigma 3 minus of minus sigma 2 divided by 2 is equal to 0. Okay, plus sigma 2 divided by 2, and tau max is equal to sigma by 2 is equal to SYC divided by 2. So sigma is equal to SYC. So this is the maximum distortion energy theory, which is also called as the von Mises Henke's theory. In this theory, it is assumed that the failure or yielding occurs at a point, the member where distortion strain energy, also called shear strain energy per unit volume in a biaxial stress system, reaches the limiting distortion energy, that is distortion energy at a yield point per unit volume as determined from a simple tension test. So maximum distortion energy is the difference between the total strain energy and the strain energy due to uniform stress. So maximum distortion energy theory, von Mises and Henke's theory. Look at this one. So here, element with the triaxial stresses, stress component due to distortion of element, then stress components due to change of the volume. So sigma 3, sigma 2, sigma 1, sigma 3d, sigma 2d, sigma 1d. Then maximum distortion energy theory, that is the criteria of failure for the distortion energy theory is being expressed as SYT is equal to square root of 1 by 2 in bracket sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. So considering the factor of safety, SYT divided by FOS, factor of safety, is equal to square root of 1 by 2 sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. So for biaxial stresses, sigma 3 is equal to 0. SYT divided by factor of safety is equal to square root of sigma 1 square plus sigma 2 square minus sigma 1 sigma 2. Maximum distortion energy theory, that is von Mises and Henke's theory. A component subjected to the pure shear stresses and the corresponding Mohr circle diagram is being shown. That is a Mohr circle diagram for the pure shear stress. You can see here tau, which is placed here, sigma 1 on the x and minus 2 minus sigma 2 on the y x axis. This is element subjected to the pure shear stresses. So from the figure, what we can see that sigma 1 is equal to minus of sigma 2 is equal to tau, and sigma 3 is equal to 0. Substituting the values in the equation, SYT divided by FOS is equal to square root of sigma 1 square plus sigma 2 square minus of sigma 1 into sigma 2. So we get SYT is equal to square root of 3 tau. So by replacing the tau by SSY, we get SSY is equal to SYT divided by root 3 is equal to 0.577 SYT. In the biaxial stress case, principal stress sigma 1, sigma 2 are calculated based on the sigma x, sigma y, and tau xy, which in turns are used to determine whether the left hand side is more than right hand side, which indicates failure of the component. So these are the four cases which is being put over here. The case number one, that is sigma 1 and sigma 2 are positive and equal to the sigma. Then SYT divided by FOS is equal to square root of sigma 1 square plus sigma 2 square minus sigma 1 into sigma 2, where sigma is equal to F SYT divided by FO, factor of safety. And in the second case, if you see here, here sigma 1 is negative and sigma 2 is positive, equal to the sigma, then SYT divided by FOS, it comes out to be equal to the square root of sigma 1 square plus sigma 2 square minus sigma 1 sigma 2. So SYT divided by FOS is equal to square root of sigma 1 square plus sigma 2 square plus sigma 1 sigma 2. SYT divided by FOS is equal to square root of 3 sigma square, so is equal to root of 3 sigma. So sigma is equal to 0.5777 SYT divided by FOS. So case 3, third quadrant, that is sigma 1 is negative and sigma 2 is positive and equal to the sigma, then SYT divided by FOS is equal to sigma 1 square plus sigma 2 square minus sigma 1 sigma 2, and sigma is equal to SYT divided by FOS. So case 4, that is fourth quadrant, sigma 1 is positive and sigma 2 is negative and equal to sigma, then SYT divided by FOS is equal to sigma 1 square plus sigma 2 square minus sigma 1 sigma 2. So sigma is equal to 0.77 S by T divided by FOS. So boundary for distortion energy theory under the biaxial stresses. Now taking an example ahead, let me check whether it is going on correctly or not. Yes, it is going on perfectly. Example of this one, that is you can see the element which is subjected to the sigma 1 35 megapascal, sigma 2 minus 25 megapascal, and still SY is equal to 100 megapascal. So minus 100 minus 100 to the 100 from negative to the positive. Similarly, shear diagonal, that is sigma 1 is equal to minus of sigma 2 minus 100 into 100 minus 100. So this is nothing but the shear stress theory. This is nothing but the normal stress theory. And the boundary, you can see that shear stress theory, which is shown in the dotted line. So load point, load line, that is this is load line, this is shear diagonal, maximum shear stress, maximum distortion energy theory, maximum normal stress th. So square root of sigma 1 square plus sigma 2 square minus sigma 1 sigma 2 less than is equal to sy. Then maximum strain energy theory or the high theory. So failure is assumed to take place at a point in a member where strain energy per unit volume in a biaxial stress system reaches the limiting strain energy, that is strain energy at yield point per unit volume as compared from a single simple test. So simple tension test. So strain energy per unit of volume in a biaxial system is basically given by an equation u1 is equal to 1 by 2e in bracket sigma 1 square plus sigma 2 square minus 2 sigma 1 sigma 2 divided by m. The limiting strain energy per unit of volume for yielding to determine from the simple tension test, that is u2 is equal to 1 by 2e in bracket syt divided by fos whole square. So equating the above two equations, then we get sigma 1 plus sigma 2 square minus 2 times of sigma 1 minus sigma 1 into sigma 2 divided by m is equal to syt divided by fs whole square. In the biaxial case, sigma 1 and sigma 2 are calculated best as the sigma 1, sigma x, sigma y, and tau xy. It will be check whether the left hand side of the equation is less than side of the equation, right? Right hand side of the equation or not. And this theory is used for the ductile material. Then fifth topic in this failure theories, that is maximum principal strain theory or the Saint Venant's theory. It is assumed that the failure or yielding occurs at a point in a member where the maximum principal, that is normal strain in a biaxial stress exceeds limiting value of the strain at yield point as obtained by the final simple tension test. So, in a biaxial stress case, E max is equal to sigma 1 divided by E minus sigma 2 divided by ME is equal to SYT divided by factor of safety into E. One can calculate the sigma 1 and sigma 2 given the sigma x, sigma y, and tau xy values, and we need to check whether the fundamental material it fails or not. Okay, whether the material it fails or not. So this theory is not used in general or as a reliable result, but could not be retained in variety of materials. So maximum principal stress theory, strain theory, that is Saint Venant's theory, it may be considering the whether the material fails or not, and this theory is not reliable. So in a biaxial stress, Emax is equal to sigma 1 divided by E minus sigma 2 divided by M into E is equal to sigma YD divided by FOS into E. Now, example of this failure theories: the load on a board consists of an axial pull of 10 kilonewton together with a transverse shear force of 5 kilonewton. Find the diameter of the bolt required according to the maximum principal stress theory, maximum shear stress theory, maximum principal strain theory, and maximum strain energy theory or maximum distortion energy theory. Permissible tensile stress at the elastic limit is equal to 100 MPa and Poisson's ratio is zero point 0.3. So this example is being given to you where the load on the bolt it is consisting of an axial pull of 10 kilonewton together with a transverse shear force of 5 kilonewton, and we have to find the diameter of the bolt required. What should be the diameter of the bolt which is being required? And according to the maximum principal stress theory, maximum shear stress theory, maximum principal strain theory, maximum strain energy theory, and maximum distortion energy theory. So permissible stress at the elastic limit is equal to 100 MPa megapascal and Poisson ratio is zero point 0.3. So cross-sectional area of the bolt which can be calculated as A into pi by 4 d square. So it coming out to be 0.478454 d square. Then axial stress is equal to sigma 1 is equal to P by A. So 10 divided by 0.7854 d square is equal to 12.73 divided by d square kilonewton per mm square. And transfer shear stress is equal to tau is equal to PS divided by A is equal to 5 divided by 0.7854 d square. Hence, tau is equal to 6.36 kilonewton per mm square. According to the maximum principal stress theory, the maximum principal stresses that is sigma 1 is equal to sigma x divided by 2 plus square root of sigma is divided by 2 whole square plus tau square xy, and sigma 1 is equal to sigma x plus sigma y divided by 2 plus in bracket sigma x minus sigma y divided by 2 whole square plus 6, and sigma 1 is equal to 12.3 d1 square plus square root of 12.73 divided by 2d square to the power of cube, and then the finally sigma 1 is equal to 153.65 divided by d square newton per mm square. So according to the maximum principal stress theory, SYT is equal to sigma 1. So therefore 100 is equal to 15365 divided by d square. So diameter of the bolt is coming out to be 12.4 mm. Sorry, yes, mm. Then according to the maximum shear stress theory, maximum shear stress theory equation proposed is tau max is equal to square root of sigma x minus sigma y divided by 2 whole square plus tau square xy. So tau max is equal to 6x by 2 whole square plus tau square xy. So 12.73 divided by d plus 6.365 divided by d square to the power of 2. So tau max is equal to 9 by d square kilonewton per mm square is equal to 9000 divided by d square newton per mm square. So according to the maximum shear stress, the tau max is equal to SYT divided by 2 is equal to 9000 divided by d square is equal to 100 by 2. So d is equal to 13.42 mm. Then according to the maximum principal strain theory, the maximum principal stress that is given by the equation sigma 1 is equal to sigma x plus sigma y divided by 2 plus in bracket sigma x minus sigma y divided by 2 whole square plus tau square xy. So sigma 1 is equal to sigma x divided by 2 plus whole square sigma x divided by 2 square plus tau square xy, that is 15365 d square, and maximum principal stress is equal to sigma 2 is equal to sigma x plus sigma y divided by 2 minus square root of sigma x minus sigma y divided by 2 whole square plus tau square xy. So sigma 2 is equal to, given by the equation, sigma x divided by 2 minus square root of, okay, minus square root of sigma x divided by 2 whole square plus tau square xy. So it is coming out to be 12.73 divided by t square minus square root of 12.73 divided by 2d square whole square plus 6.365 divided by t square to the power of 2. So sigma 2 is minus 2635 divided by t square Newton per m square. So according to the maximum principal strain theory, the sigma 1 minus sigma 1 minus e, so, minus sigma 2 divided by me plus minus sigma 2 is equal to syt divided by e, where sigma 1 minus sigma 2 by m. So sigma 1 minus sigma 2 divided by m is equal to syt is equal to 15365 d square plus 2635 into zero point 0.3 divided by d square plus 100. So diameter coming out to be 12.7 mm. Then according to the maximum strain energy theory, the sigma 1 square plus sigma 2 square minus C2 sigma 1 sigma 2 divided by m is equal to 2yt square. So here the equations you can see that how you used to that diameter is being given, that is 12.7 m. Average the value of according to the maximum distortion theory. So SYT is equal to, in bracket, sigma 1 square plus sigma 2 square minus sigma 1 sigma 2. So keeping the value of 100 as a SYT, 100 is equal to square root of 153.65 divided by d square to the power of, then minus 2365 divided by d square to the power of to the whole square minus 15365 divided by d square minus 1 minus 2635 divided by d square. So d is equal to 13.4 mm. So now we will see the fatigue strength and analysis. Yes, it is going on. 1 minute break and then we will continue. Then fatigue strength and analysis, the definition of terms, that is a fracture. So a fracture is the local separation of an object or material into two or more definitions. So definition in fracture mechanics, a process of forming new surface through irreversible process under the mechanical load. So what do you mean by the fracture mechanics? Fracture is basically the local separation of an object or a material into two or more parts. So definition of the fracture mechanics, it is the process of forming a new surface through irreversible process under mechanical load. And failure means that a machine fails to perform. Okay, the term of failure is widely used in reliability engineering. It may happen even without the destruction. So here you can see that damaged airplane left and a fractured fan hub on the right hand side. So this is the fractured fan hub, and this is the damaged airplane you can see. So classification of the fracture types. So what are the classification of fracture type? No apparent plastic deformation takes place before the fracture, but once fractured, the crack propagates rapidly in case of the brittle material, and once fractured, the destruction continues to proceed after the force removal in case of the brittle material that is happening. Then classification of fracture type: ductile fracture, that is a extensive plastic deformation takes place before the fracture. That happens in the ductile fracture, that is extensive plastic deformation takes place before fracture. Relatively slow and stable crack propagation is stable in that cracks are in equilibrium at each point. So propagation stops when a load is removed and an extra load must be applied for further crack propagation. So a pipe ductile fracture, left one piece and a large deformation. Brittle fracture, right many piece from the small deformation. So crack propagation is stable, and in that the cracks are in equilibrium at each point. So propagation stops when a load is removed, and an extra load must be applied for further crack propagation. Then the fatigue fracture. So you can see the Aloha Airlines flight 243 Boeing 237 737 200 April 8, 1988, uh, and Honolulu, Hawaii also. Undetected cracks in full fuel skin and corrosion in the joint as a result of disbanding. So fatigue fracture, general definition of the fatigue fracture: a destruction as a result of the repeated loading and unloading. And definition in ASTM, that is American Society for Testing and Material. It is the process of progressively localized permanent structural change occurring in a material subjected to the conditions that produce fluctuating stresses and strains at some point or points, and which may culminate in cracks and complete fracture at a sufficient number of fluctuation. So the fatigue fracture, that is the destruction basically as a result of repeated loading and unloading. Fatigue fracture generalization: a material received external or internal repeated loading, cyclic loading, changes in local organization due to the repeated load eventually leads to cracks or fracture process. Then classification of the fracture types, that is creep fracture, the time dependent deformation even with a constant load at over a certain temperature. Creep deformation accelerates at some point resulting in the rupture. Here the strain is there. Here creep deformation, constant rate, single step 1, primary creep, step 2, secondary creep, rupture. This is stage 3, territory creep. Stage 1, primary creep, stage 2, secondary creep. You can see in third one, stage 3, territory creep. And here the point, the rupture is taking place. So delayed fracture and environment assisted fracture. Even though a static tensile stress is much lower than the yield stress, the mechanical material behaves more brittle and thus suddenly ruptures without apparent plastic deformation. So environment assisted fracture is also called as environment sensitive fracture. Then the fracture types and the basically the material strength. What do you mean by the strength of material? That is, strength of the material is considered in two cases: with and without flaws or cracks. Basic strength is normally without flaws. Fatigue strength. Fatigue is very important in terms of the strength of material, and fatigue strength is one of the important parameters in the mechanical design. So, relationship between the fracture type and material strength: ductile fracture, brittle fracture, or static strain, fatigue fracture, fatigue strain, then creep fracture greater than the creep strain or high temperature. So when material receives repeated loads at high temperature, for example, in case of the thermal stresses. So stress corrosion cracking, hydrogen entanglement cracking, and environmental strain. So this is the relationship between the fracture type and the material strength. Characteristics of the fatigue fracture, that is cyclic loading. Fatigue occurs as a result of repeated loading and unloading. All the machines and structures get cyclic loading in nature, so most of the fracture result from the fatigue only. Lower yield stress of the proportional limit, that is, although cyclic stress range is smaller than static fracture stress or yield stress, fatigue fracture occurs. So fatigue limit or endurance limit, that is fatigue limit and endurance limit are the endurance limit are all expression used to describe a property of material, the amplitude of cyclic stress that can be applied to the material without causing the fatigue failure. So look at these pictures. Example of fatigue failure. Enrollment of the region indicated by white arrow in the left picture. Final torsional overload, fracture origin, intergranular fracture, zone 1 and zone 2. So macroscopic features of the fracture surfaces. On the surface of fatigue fracture, microscopic features exist. By examining the fracture surface, we can estimate the cause of the fracture, the location of the crack, and the amplitude of the load. So, example of the fatigue failure accident, that is crash of the world's first commercial jet Comet, 1954. Yeah. The crash of the BOAC Comet on 10 January 1954. The aircraft went down into the sea of the Elba 20 minutes after taking off from the Rome. So, crash of the world's first commercial jet Comet in 1954. The plane, British Overseas Airways Corporation jet Comet, was crashed on its way from Rome to London. Okay, accident cause fuel usage damage caused by fatigue fracture occurred at the corner of a automatic direction finding window in the upper part of the fuel usage. Casualties 29 passengers and 6 crews died. After the experimental study to find the failure cause, full scale fatigue testing and low cycle fatigue testing have become the crucial. So SN diagram, you can see here the number of stresses, number of stress cycles, and fatigue strength, that is KPSI, low cycle, and this is the high cycle, finite life, infinite life. So stress levels below AC predict the infinite life. 10 to the power of 3, 10 to the 2, 10 to the power of 6 cycle is finite cycle. Below 10 to the power of 3 low cycle, so that is quasi-static, and yielding usually occurs before the fatigue. This is SN diagram for the steel. Then SN diagram for non-ferrous metal. You can see here life, that is n number of cycles, log, and peak alternating bending stress. So no endurance limit, fatigue strength. SN diagram for aluminum, rot, aluminum mold cast, sand cast. So this is the SN diagram for the non-ferrous material where there is a no endurance limit, fatigue strength is SL, and SN diagram for aluminum. The detailed analysis of plastic deformation at localized region, that is stress line method. Then then compounding of several idealizations lead to significant uncertainties in numerical result and useful for explaining the nature of the fatigue. Then strain-like method, that is fatigue failure begins at local discontinuity. So here you can see that it is beginning at the local discontinuity. When stress at the discontinuity exceeds the elastic limit, plastic strain occurs. So in this case, the cyclic plastic strain can change the elastic limit, leading to the fatigue. Then relationship of fatigue like to strain. The figure one relationship of basically the fatigue life to the true strain amplitude, then fatigue ductility coefficient, true strain at which fracture occurs in one reversal, point A in figure 2, and fatigue strength coefficient, true stress corresponding to fracture in one reversal, point A in figure 2. So these are the strain amplitude, reversals to failures, elastic strain, plastic strains, and the total strain. So the relationship of fatigue like to strain, equations of plastic strain line in shown in figure, that is delta P divided by 2 is equal to sigma F epsilon F 2n, equating the equation of elastic strain line, that is it comes down to be delta E divided by 2 is equal to sigma F divided by E into 2n b to the power of b plus sigma F, that is 2n to the power of c. Then relationship of fatigue life to strain, that is ductility exponent, the slope of plastic strain line, 2n stress in reversal, and fatigue strength exponent, slope of the elastic strain line. Then relationship of fatigue life to strain, that is delta E divided by 2 is equal to sigma F divided by E 2n to the power of P. Manson coffin relationship between the fatigue life and the total strength. Table 823 values of coefficient and exponent. Equation has limited use for the design. Values of for total strain at discontinuous are not readily available. Then the endurance limit, you can see the plot for the three material, that is carbon steels, alloy steels, and the wrought iron, and it is being plotted with respect to the tensile strength, SUT, and the endurance limit. Carbon steel, alloy steel, and wrought iron. Then simplified estimate of endurance limit for steels for the rotating beam specification specimen, that is SC is equal to zero point 0.5 SUT, that is endurance limit, simplifications relationship, that is SUT should be lesser than or equal to 20 kpsi, that is 1400 megapascal, and 100 kpsi SUT is greater than 200 kpsi, and 700 MPa megapascal is equal to SUT greater than 1400 MPa. Fatigue strength for design and approximation of the idealized SN diagram is desirable. To estimate fatigue strength at 10 to the power of 3 cycle, start with the equation 6.2. So delta E2 divided by delta F E 2n to the power of B. Define specimen fatigue strength at a specific number of cycles. So SFN is equal to E. At 10 to the power of 3 cycles, F is equal to fraction of SUT. So fraction of SU2 is equal to SF 10 to the power 3. And here sigma F is equal to SUT plus 50 kpsi. Sigma F is equal to SUT plus 345 uh, MPa. To find the B, substitute endurance strength and corresponding cycles into the equation 6.9 and solve for B, that is B is equal to minus of log of sigma F divided by SC divided by log of 2n. So Sfn is equal to sigma F 2n to the power of B. Then finding out this equation, that is substitute equation 6.11 and 6.2 into equation 6.9 and 6.10. 6.9 and 6.10 are being shown here, and to obtain the expression for SF and F. So fatigue strength fraction F, plot versus SUT. So plot equation for the fatigue strength for fraction for fraction of F of SUT at 10 to the power 3 second. So use F from the plot, that is for SF is equal to F of SUT at 10 to the power of 3 cycles on SN diagram, and assume SC is equal to zero point 0.5 SUT at 10 to the power of 6 cycle. So equations for the SN diagram, fatigue strength versus the number of cycles, low cycle, high cycle, finite life, and infinite life is being given. Then equations for the SN diagram, write equations for the SN line from the 10 to the power of 3. So equations for the SN diagram, Write equation for SN line from 10 to the power of 3 to 10 to the power of 6 cycles. So two known points, that is at n is equal to 10 to the power of 3 cycles, and SF is equal to f of SUT, and at 10 n is equal to 10 to the power of 6 cycle, SF is equal to AC. Equations for line SF is equal to a n to the power of b is equal to a is equal to f of SUT whole square divided by AC. So b is equal to minus of 1 by 3 log of f SUT divided by AC. If a completely reverse stress sigma reversible is being given, setting SF is equal to sigma revolves, and solving for n gives n is equal to sigma ReV divided by A to the power of 1 by P. So typical Ascent diagram is only applicable for completely reverse stresses. Ascent diagram is completely applicable for extremely completely reverse stresses. For other stress minimization, a completely reverse stress with the same expectancy must be used on the Ascent diagram. Low cycle fatigue. So when n is greater than 1 and less than 10 to the power of 3. So on the idealization diagram on a log scale, the failure is predicted by a straight line between the 2 points, that is 10 to the power of 3, okay, uh, comma f of SUT and 1 comma SUT. So SF is greater than SUT n to the power of log of f by 3. So n lies between 1 and 10 to the power of 3. So given a 1050 HR still estimate the rotating beam endurance limit at 10 to the power of 6 cycles. The endurance strength of a Polish rotating beam specimen corresponding to 10 to the power of 4 cycles to failure, and the expected life of a Polish rotating beam specimen under a completely reverse stress of 55 kPa. So endurance limit SE is carefully prepared and tested specimen. If warranted, SE is obtained from testing of actual part. When testing of actual part is not practicable, a set of marine factors are used to adjust the endurance limit. So these are the some of the gate questions based on the theories of failure, like match the correct pairs of the between the list. What is being given, that is Hooke's law, Saint Venant's law, Kepler law, Trisca's criteria, Columbus law, Greer's law, so planetary motion. So it is Saint Venant law, that is maximum principal strain theory. That is Kepler's law, because Hooke's law is related with the elasticity. Then Saint Venant's, Kepler's law is related with the planetary motion. D, that is Tresca criteria related with the fracture. The stress state at a point of in a body in play is plane with 22 into 2 sigma 12 is equal to minus 60 Newton per mm and sigma 36 Newton per mm. If the allowable stress for the material in simple tension or compression is 100 Newton per mm square, calculate the value of factor of safety with each of the following criteria. And so maximum stress criteria, maximum shear stress criteria, maximum stress criteria, maximum distortion energy criteria. Okay. So stress at a point in a body is a plane, that is sigma is equal to minus 6. Which theory of failure will you use for aluminum components under steady loading? Principal stress theory, maximum principal strain theory, or strain energy due to or strain energy theory, or maximum shear stress theory. So, which theory of failure will you use for aluminum components under steady loading? So, aluminum is a ductile material, so we use the maximum shear stress theory. Similarly, which of the one of the following is the most conservative failure fatigue failure criteria? Soderbergh criteria, or modified Goodman criteria, or ASME elliptic, or Kerber criteria. So Soderbergh criteria is the most conservative fatigue fracture criteria. A fatigue strength of a rod subject to a axial load is less than that of a rotating beam of the same dimensions subjected to the steady lateral force beam, because axial stiffness is less than the bending stiffness of absence of centrifugal. Then what is the option? The number of discontinuities vulnerable to fatigue are more in the rod. Then the process of hot short spinning increases the fatigue life of steel springs, mainly because it results in a surface hardening, increased stiffness, metal. Means the process of short spinning increases the fatigue life of the steel springs, mainly because it results in the residual compression at the surface. So, with this, we have completed a topic of theories of failure. Okay, let me give you some more practice numerical on the theories of failure. Yes. So I hope that my screen is visible to you. So, which theory of failure will you use for aluminum components under steady loading? So, which theory of failure we are going to use for aluminum components under steady loading? So, aluminum is nothing but the ductile material. Whether you use the principal stress theory, principal strain theory, strain energy theory, or maximum shear stress theory. So, answer is correct. That is maximum shear stress theory. A solid shaft can resist a bending moment of 3.0 kilonewton meter and a twisting moment of 4.0 kilonewton meter together. Then the maximum torque that can be applied. What is the maximum torque that can be applied? Because this shaft can resist a bending moment of 3 kilonewton meter. So if you see here, two shafts A and B are they are made up of the same material. The diameter of shaft B, okay, is twice as that of shaft A. The ratio of power which can be transmitted by shaft A to that of shaft B is 1 by 2, okay, 1 by 4, 1 by 8, 1 by. So here 5 kilonewton meter is there. So here two shafts are made up of the same material, and the diameter of shaft B is twice of that of the shaft A. The ratio of power which can be transmitted by the shaft A to the shaft B is nothing but the 1 by 8. Similarly, the outside diameter of a hollow shaft is twice the inside diameter. The ratio of its torque carrying capacity so that a solid shaft of the same material and the same outside diameter, it will be 15 by 16. Okay. Okay. Another questions. The principal stresses at a point inside a solid object are sigma 1 is equal to 100 MPa, sigma 2 is equal to 100 MPa, and sigma 3 is equal to 0 MPa. The yield strength of the material is 200 MPa. The factor of safety calculated using the Tresca, that is maximum shear stress theory, is NT, and the factor of safety calculated using the one misses maximum distortion energy theory is in which of the following relation is true? To select any answer, study. So, what is our answer? That is NT Aderma. So, from the subject, that is failure. Which one of the following is the most conservative fatigue failure criteria? So, here, Soderbergh, most common conservative failure connection. Soderbergh. A machine element is subjected to the following biaxial state of the stress: sigma x is equal to 80 MPa, sigma y is equal to 20 MPa, tau xy is equal to 40 MPa. So, in this kind of element, if you see the answer, it is 2. Measures. So, the uniaxial yield stress of a material is 300 megapascal. According to the one Mises criteria, the shear stress in the MPa of the material is 170. Which one of the following statement is not correct and intermediate principal stress is ignored? Gate 2015 it was asked for the 1 mark. So here the maximum shear stress theory gives the most accurate result amongst all the failure theories. So likewise you have to solve the numericals based on this particular topic of theories of failure. Okay. Now I will take up the another topic for my today's presentation. So, so let me start the topic of refrigeration and air conditioning. We will take a 1 minute break and then we will continue with the refrigeration cycle. So, the refrigeration cycle. Today, we will start now this topic basically the refrigeration cycle. All of you are aware that the refrigeration cycle, refrigeration and air conditioning is used in the household. So, in the household application or in the industrial application also, these refrigerators are used and the refrigeration cycles are also used. So, as a mechanical engineer, the knowledge of the refrigeration cycle or the air conditioning system is very essential. So, introduction to the refrigeration of the cycle and the equipment. After completing this chapter, that you will be able to know the apply the general principles of mechanical engineering, then absorption and refrigeration, and explain how refrigerants absorb and rejects heat. Arrange the basic mechanical refrigeration cycle component in the proper order. Describe the operating characteristics of various types of compressors. So, describe the air and water cooled condenser, describe the various metering and expansion devices, describe the characteristics of DX coils and liquid chiller evaporator. Okay, then describe the operation of the absorption refrigeration cycle. So this is what the what we are going to study today regarding the refrigeration and air conditioning cycle and equipment. So introduction to the refrigeration cycle and equipment. What is the general principle of refrigeration? It is the process of extracting heat from a substance or the window air conditioner means suppose if any product is there at a temperature of 30 degrees centigrade, then if you want to wish to extract the heat from the that product by applying some cases by applying something, then in that case this is nothing but the extracting the basically the heat from the substance so that it can be made it can be maintained at the cool temperature or the controlled temperature. So window air conditioners and central systems absorb heat from the occupied space. For example, the air conditioning systems that if the air conditioner is being installed in any room or in any hall, then it is extracting the heat from the hall, extracting the heat from the room, okay, and keeping this space in the air basically, and that is the air conditioning. For example, in a room also, when we use the basically the air conditioner, it maintains the temperature inside the room. Now transfer this heat to the outside area because this heat which is being absorbed by the refrigerant which is circulated through this one circulated through the that is a refrigeration cycle. Then once this heat is extracted from the substance or from the area where the or the space to be cooled, then it is to be transferred to the atmosphere. So transfer this heat to the outside area. So larger system but rely on the same principles. So refrigeration capacity that is rated, it is given in rated in terms of refrigeration effect. So 1 ton of refrigeration is nothing but 144 British thermal unit divided by LB, per LB into 2000, it is equal to 202 lakh and 88,000 BTU per day. So 1 ton is equal to 12,000 BTU per hour. For example, the system capacity is equal to 1200,000 BTU per hour. So this 1200 thousand 1,200,000 divided by 12,000 is 100 ton. So refrigerant, what does the refrigerant is doing? It absorbs the heat by evaporating a low temperature and a pressure. Okay, and reject the heat by condensing at a higher temperature and a pressure, which means that refrigerant it basically absorbs the heat by evaporation and at a low temperature and then the pressure and then reject the heat in the condenser at a higher temperature and pressure. Halogen refrigerants are commonly used in mechanical refrigerant systems. There are various types of refrigerants. Nowadays, even the eco-friendly refrigerants are available so that there should not be any ozone layer depletion from the refrigerants which is used in the refrigerator. But there are several types of refrigerant which are customized, which are used in the refrigeration cycle. Then temperature pressure relationship of refrigerant. Pressures are changed in order to change the saturation temperature of the refrigerant, and the PT chart provide the basically the pressure temperature chart. They provide the relationship between the temperature and pressure of the various refrigerant. So, basic mechanical refrigeration cycle, it consists of that is simple Weber compression cycle will be there. So it consists of the compressor, then condenser, then metering device, and the evaporator. What is the function of the compressor? That is, it raises the temperature and pressure of the refrigerant. Then condenser, it removes the heat that was added to the system by the evaporator. and the compressor and metering device controls refrigerant flow to the evaporator. So evaporator, that is heat absorbed from the space. Then compressors, there are compressors, that is a reciprocating compressor equipped with the piston and cylinder, suction and discharge valve. Valve position is controlled by the pressure difference across it. It can be open or semi-hermetic or the fully hermetic compressor. So there are various types of compressor depending upon the particular application, specific application. The compressor is selected for use. Rotary compressor, hermetically sealed rotary compressors are also used. It uses the circular motion to obtain the compression. So rotating blade system is there, vent type, and refrigerant is trapped by the rotating vanes. So refrigerant compresses as volume decreases. So stationary blade vent type, which are equipped with only the one blade or the vane. Then helical type of compressor or screw type compressor, it utilizes the two rotors, a male and a female rotor. So compressor capacity controlled by a slide valve. A continuous flowing output is produced and the volume of the refrigerant decreases as it flows through the compressor. This is regarding the helical rotary screw type compressor. Then introduction to the refrigeration cycle equipment, that is compressors. The scroll type compressor, it utilizes the two identically machined scrolls. One scroll is stationary and the other orbits. The nesting of the scrolls traps the vapor and gas is introduced from the outer edge. So refrigerant is discharged from the center. So centrifugal type of compressors, they rely on the centrifugal force. No pistons are there, no valves are there, or cylinder. It utilizes an impeller. Capacity is controlled by inlet vanes used for very large applications. Then coming to the air-cooled compressor, that is in this air-cooled compressor, the desuppurating, that is removes the sensible heat, superheat from the vapor refrigerant. Then condensing, that is vapor condenses into a liquid, that is latent heat. Subcooling, addition sensible heat is removed from the liquid refrigerant. Water cooled condenser, shell and tube type. Water circulates through the tubes in the shell and tube condenser. Water makes several passes before exiting, and hot gases enter the shell and the condensers and mechanically cleanable water cooled condenser. Shell and coil type of condenser, it is similar to the shell and tube, and these are used in the small applications. Tubes are now in a coil shape and they must be cleaned chemically. Tube within a tube, that is water flows in the inner tube, refrigerant flows in the outer tube. Heat travels from the refrigerant to the surrounding air and to the water in the coil. So this kind of condenser is being called as the tube within a tube. Then evaporative condenser, it utilizes the air and the water. Air flows over the coil. Water can also flow over the coil if needed. Latent and sensible heat transfers takes place. Water is heated and the evaporated. Metering devices, thermostatic expansion valve, that is constant pressure expansion valve, the capillary tube, high float, side float, or reflex fluid. So these are the metering devices which is being used. Thermostatic expansion valve, it maintains the constant superheat in the evaporator. So three pressures control the valve position, that is bulb position, spring position, and the evaporator. As the load increases, the valve opens, and as the load increases, the valve closes. Constant pressure expansion valve. Here it maintains the constant evaporator pressure, and an increase in evaporator pressure will cause the valve to close, and the decrease in the evaporator pressure will cause the valve to open. So commonly used on systems with constant loads. Introduction to the that is capillary tubes, that is seamless tubing with a small inside diameter. No moving parts are there. No moving parts are there in the capillary tube. High side float valve introduces refrigerant to the evaporator at the same rate as it leaves. A float on the high side maintains the proper flow. Orifice plate type is also used. It is used mainly primarily on the centrifugal chiller, and two plates with a series of holes in each one. The pressure drop across the plates changes with the load, and high load liquid passes the plate, and low load the some liquid flashes to a vapor. Direct expansion coils. So direct expansion coils, the warm air passes over the cool coil. Heat is transferred to the liquid refrigerant. The liquid refrigerant begins to boil, and vapor refrigerant leaves the evaporator, and expansion valves control flow to the coil. Evaporators are the liquid chillers. Direct expansion chilled water evaporator. So refrigerant flows in the tubes, water fills the shell, then flooded shell and tube, that is refrigerant is in the shell and water flows in the tubes. So these are the evaporators for the liquid chillers. Then let us see the introduction of the absorption refrigeration cycle. In the absorption refrigeration cycle, ठीक है. So let us see. Absorption refrigeration cycle, it uses the physical properties of the absorbents, and low concentrations are weak and dilute solutions. High concentrations are concentrated, and systems use an absorbent and a refrigerant. That is, absorbent is lithium bromide and refrigerant is water. So this is the process of the vapor absorption refrigeration system. You can see that this part is nothing but the condenser. Okay, this is nothing but the evaporator, the expansion valve, and pump is placed over here. This is the absorber. This is pressure reduction valve, and analyzer or the generator. So look at it one, that is evaporator. In the evaporator, the refrigerant absorb the heat from the substance which is to be cooled, and then it goes as a low pressure ammonia vapor into the ammonia H2O solution. So in this absorber here, the strong ammonia plus H2O solution is pumped with the help of the pump into the analyzer or the generator, and here the NH2 plus H2O solution is there. So this wall is nothing but the pressure reduction wall, and from this point the high pressure ammonia vapor, it goes to the condenser. In the condenser again it rejects the heat, okay, to the atmosphere, which is cooled from the external source, and then liquid NH3, because vapors has been converted into the liquid ammonia. Liquid ammonia, it goes to the high pressure liquid expansion valve, and then it becomes the, its pressure is reduced, that is low pressure low temperature liquid ammonia. So here low pressure NH3 vapor is there, low here strong NH3 plus H2 solution is there. So this is the example of the working of the refrigeration system, vapor absorption refrigeration system. So it consists of the evaporator, absorber, concentrator, and the condenser. Okay. So these are the parts of the absorption refrigeration system. What is the function of the evaporator? Evaporator operates at a low pressure, like 25 pounds per square inch. Refrigerant, that is water, is sprayed into the shell. Conditioned liquid gives up heat to the water, and the refrigerant boils and passages to the absorber. Chilled water returns to the remote location. So this is what the function of the evaporator in the, basically the vapor absorption system, where the refrigerant boil and passes to the atmosphere, and chilled water returns to the remote location. Absorber, refrigerant from the evaporator enters the absorber. The refrigerant is absorbed by the absorber. The rate of absorption is determined by the concentration of the solution. Higher the concentration, the lower is the chilled water temperature. Then concentrated, that is dilute absorbent solution, flows to the concentrator. Okay, heat sources boil the refrigerant from the absorbent. The solution now becomes highly concentrated, and the concentrated solution, it returns to the absorber. Then condenser, used in the vapor absorption system, it is responsible for supplying liquid refrigerant to the evaporator. The refrigerant vapor leaves the concentrator, and this vapor is condensed back to the liquid state, and this liquid refrigerant returns to the evaporator. So here again you can see that the line diagram of the vapor absorption system. So refrigeration, so refrigeration is the removal of heat from a material or space so that its temperature is lower than that of its surrounding. So when the refrigerant absorbs the unwanted heat, This raises the refrigerant's temperature, which is called as the saturation temperature, so that it changes from a liquid to the gas. Okay, it changes from a liquid to the gas. It evaporates. The system then uses a condensation to release the heat and change the refrigerant back to the liquid. This is called as the latent heat. This cycle is based on the physical principle that a liquid extracts heat from the surrounding area as it expands or boils in the gas into gas. To accomplish this, refrigerant is pumped through the closed loop pipe system, and the closed loop pipe system stops the refrigerant from becoming contaminated and controls the stream. The refrigerant will be both vapor and liquid in the loop. Then saturation temperature, which is defined as the temperature of a liquid vapor or a solid, where if any heat is added or removed, a change of the state takes place. So change of the state transfer. So change of the state transfer a large amount of energy. If saturation pressure materials are sensitive to additions or removal of heat. Water is an example of low saturation property of a material. It can transfer a large amount of heat. Refrigerants use the same principle as ice. For any given pressure, refrigerant have a saturation temperature. If the pressure is low, the saturation temperature is low. If the pressure is high, saturation temperature is also high. So latent heat, the heat required to change a liquid into a gas, is called as the latent heat, or the heat that can be removed from the material, removed from the gas. Latent heat that must be removed from the gas to condense it into a liquid without any change in the temperature. So heat is a form of energy that is transferred from one object to the another object, and heat is a form of energy transferred by a difference in temperature. So heat transfer can occur when there is a temperature between the so heat transfer can occur when there is a temperature difference between the two or more objects. Heat will only flow from a warm object to a colder object. The heat transfer is greatest when there is a large temperature difference between the two objects. There are main four components of the vapor compression cycle. Okay, the compressor, then the condensing coil, the metering device, and the evaporator. So you can see here the compressor. The two different pressures exist in the refrigeration cycle. The evaporator or the low pressure. So this is your evaporator or the low pressure in the low side of the and the condenser or high pressure in the high side of in the high side. These pressure areas are divided by the other two components. On one end is the metering device which controls the refrigerant flow, and on the other hand is the compressor. So here look at this picture. This is compressor. Okay, and then the compressed refrigerant it goes to the evaporator. In the evaporator, refrigerant absorbs the heat basically from the substance which is to be cooled, which is to be placed. Again, it get heated. Conversion of phase is being going on, liquid to vapor, and then through the filter dryer, it is being supplied to again the condenser. Then in the condenser, it rejects the heat to the atmosphere, and further, the again it comes back to the compressor. So the compressor is the heart of the system. The compressor does just what its name is. It compresses the low pressure refrigerant vapor from the evaporator and compresses it into a high pressure vapor. Okay. So This is the function of the compressor. The inlet to the compressor is called the suction line. It brings the low pressure vapor into the compressor, and after the compressor the compresses the refrigerant into the high pressure vapor. It removes it to the outlets called the discharge line. So discharge line basically leaves the compressor and runs to the inlet of the compressor. This is expansion valve, compressor, evaporator, condenser. Because the refrigerant was compressed, it is a uh, high pressure vapor. As pressure goes, as pressure goes up, temperature goes up. The hot water enters the condenser and the starts to flow through the tube. Cool air is blown across the side of the fin tubes of a condenser, usually a fan or water fin with a fin. Since the air is cooler than the refrigerant, uh, heat pumps from the tubing to the cooler air. That is, energy does not from hot to the cold. Okay, energy is from low to the cold to the hot. As the latent heat is removed from the refrigerant, it reaches its saturated temperature and starts to flash, means change states into a high pressure liquid. The high pressure liquid leaves the condenser through the liquid line and travels to the metering device, sometimes running through a simple dryer first or to remove any dirt or the practices. Metering devices demo we will see. Okay. So metering devices demo. Here liquid line in, external equalizer, evaporator, pressure from sensing bulb. Okay. So metering devices regulate how much liquid refrigerant enters the evaporator. Metering devices basically it regulates the flow of the liquid refrigerant which is entering into the evaporator. It is commonly used metering devices are small thin copper tubes which are also called as the cap tubes or thermally controlled diaphragm valves called as the TXPs, thermal expansion valve, and the single opening orifices. The metering device tries to maintain a preset temperature difference or a superheat between the inlet and the outlet openings of the evaporator. As the metering device regulates the amount of refrigerant going into the evaporator, the device lets the small amounts of refrigerant out into the line and loses the high pressure as it behind it. Now we have a low pressure cooler liquid refrigerant entering the evaporative coil. So pressure went down, so the temperature also goes down. Now the thermal expansion valve. Look at the thermal expansion valve. In the thermal expansion valve, it is a very common type of metering device which is called a TX valve. So thermostatic expansion valve. This valve has the capability of controlling the refrigerant flow. So if the load on the evaporator changes, the valve can respond to the change and then increase or decrease in the flow accordingly. If TXP has a sensing bulb attached to the outlet of the evaporator, the bulb senses the suction line temperature and sends a signal to the TXP, allowing it to adjust the flow rate. So this is important because if not all the refrigerant in the evaporator changes the state into the gas, there could be a liquid refrigerant content returning to the compressor. This can be fatal to the compressor. Liquid cannot be compressed, and when a compressor tries to compress a liquid, mechanical failing can happen. The compressor can suffer mechanical damage in the walls, and bearing, and this is called as the liquid which is struggling. Okay. So normally TXV are the, that is thermal expansion valve, are set to maintain 10 degrees of superheat. That means the gas returning to the compressor at least 10 degrees away from the risk of having any liquid. The evaporator demo, you can see that this is the part of the evaporator. Here superheated vapor here begins boiling and the finishes boiling. The evaporator is where the heat is removed from the your house, business, or the refrigeration box. Okay, and the low pressure liquid leaves the metering device and enters the evaporator. Usually, a fan will move warm air from the conditioned space across the evaporator fin coil. The cooler refrigerant in the evaporator tubes absorb the warm room air. The change of temperature causes the refrigerant to flush or boil and changes from a low pressure liquid to a low pressure cold vapor. The low pressure cold vapor is pulled into the compressor and the cycle starts over. The amount of heat added to the liquid to make it saturated and change states is called the superheat. One way to charge a system is with a refrigerant by superheat. Then review of the refrigeration cycle, how the refrigeration cycle is there. That is starting the compressor. In the beginning, you have to start the compressor. Then low pressure vapor refrigerant is compressed and discharged out of the compressor. The refrigerant at this point is a high temperature, high pressure in the superheated region. The high pressure refrigerant flows to the condenser by the discharge line. The condenser changes its high temperature refrigerant into a low temperature low temperature vapor to a low temperature high pressure liquid and leaves through the line. The high pressure refrigerant then flows through a filter dryer to the thermal expansion valve and thermal expansion meters to correct the amount of liquid refrigerant into the evaporator. As TXV meters the refrigerant, the high pressure liquid changes to a low pressure or low temperature saturated liquid vapor. And a saturated liquid vapor, it enters the and change to a low pressure dry vapor. The low pressure dry vapor is then returned to the compressor in the suction line. Then the cycle again start over. So this is the review of the simple vapor compression system. Okay, we will take a small break and we will continue again. The vapor compression refrigeration cycle is a common method. uh, so from vapor compression refrigeration cycle, which is a common method for transferring the heat from a low temperature to a high temperature. You can see here, this is the cold or the refrigerator space, and from here, the by providing the required input, we take out the heat, and then this heat is rejected to the warm environment. Okay, heat is rejected to the warm environment. This is the refrigerator, and the heat pump, that is cold environment is there, and required input is provided so that that is heat is being pumped, and then from the cold environment, and then it is being supplied to the farmhouse. The above two figures, they shows the objectives of the refrigerators and the heat pump. The purpose of the refrigerator is the removal of the heat called the cooling load from a lower temperature medium, and the purpose of the heat pump is the transfer of the heat to a high temperature medium called the heating load. So when we are interested in the heat energy removed from a lower temperature space, the device is called a refrigerator. And when we are interested in the heat energy supplied from a high temperature space, the device is called a heat pump. So in general, the term of the heat pump is used to describe the cycle as the heat energy is removed from the low temperature space and rejected to the high temperature space. The performance of the refrigerators and heat pumps is expressed in terms of the coefficient of performance. So, how it is being expressed, that is COP of the refrigerator is equal to desired output divided by required input is equal to cooling effect divided by work input is equal to QL divided by W net in. So COP of the heat pump is nothing but desired output divided by required input, and heating effect divided by work input. This difference will be there. So COP of a refrigerator is nothing but the QL divided by the W net. Both COP of refrigerator and COP of HP can be larger than 1. Under the same operating condition, the COPs are related by COP of heat pump is equal to COP of refrigerator per 1. Can you show this is to be true? Because refrigerators, air conditioners, and the heat pumps are rated with a SEER number or season adjusted energy efficiency ratio. Seasonal adjusted energy efficiency ratio. SEER is defined as the BTU per hour of unit, BTU per hour of heat transferred per watt of work in energy input. The BTU is the British thermal unit and the equivalent of 778 FTLB of work. So 1 W is equal to 3.4122 BTU per hour. So an ER of 10 yields COP of 2.9. Refrigeration systems are also rated in terms of tons of refrigeration. So 1 ton of refrigeration is equivalent to the 12,000 BTU per hour or 211 kilojoule per minute. How did the term ton of cooling originate? Okay. So reverse cannot refrigerator and the basically the heat pump. So in this case, if we see here, it is shown today below are the cyclic refrigeration devices operating between the two constant temperature reservoirs, and the temperature entropy diagram for the working fluid when the reverse Carnot cycle is used. So recall that in the Carnot cycle, heat transfer takes place at a constant temperature. So if our interest is in the cooling load, the cycle is called the Carnot refrigerator. Okay, if our interest is in the heating load, the cycle is called the Carnot heat pump. So here the cold medium, evaporator, then turbine, condenser, the rejecting the heat to the warm medium, compressor, compressing the refrigerant and delivering the liquid refrigerant to the evaporator. So this is your temperature entropy diagram. So 1 to 2 is nothing but the evaporator where the heat is extracted from the substance to be cooled, and then the refrigerant phase changes from basically liquid to the vapor refrigerant. Then from 2 to 3 is nothing but the compression, the process which is constant entropy process carried out in the compressor. Then 3 to 4 again it is nothing but the condensation where heat of the refrigerant, high pressure refrigerant is rejected to the atmosphere, and 4 to 1 is nothing but in the capillary tube where the expansion valve where it is a constant entropy, and again the temperature of the liquid it is being dropped, and here the liquid refrigerant okay is being circulated into the evaporator, and again in the evaporator it absorbs the heat from the space to be cooled or from the substance to be cooled, and then get again the vapors, and these vapors again it reaches to the compressor, and then further compression, condensation, expansion valve or capillary tube, and then evaporator. This process or this cycle continues. The standard of a comparison of refrigeration cycle is the reverse Carnot cycle. So a refrigerator or heat pump that operates on reverse Carnot cycle is called a Carnot refrigerator or a Carnot heat pump, and their COPs are calculated as COP refrigerant Carnot, COP HP Carnot, so TL divided by TH minus TL, TH divided by TH minus TL, COP of the heat pump Carnot. Notice that a turbine is used for the expansion process between the high and low temperature, while the work interactions for the cycle are not indicated on the figure. The work produced by the turbine helps supply some of the work required by the compressor from the external sources. Why not use the reverse Carnot refrigeration cycle? It is easier to compress vapor only and hot liquid vapor mixture, cheaper to have irreversible expansion through an expansion valve. So, what problem results from using a turbine instead of using an expansion valve? The vapor compression refrigeration cycle. So, vapor compression refrigeration cycle, it has main four components. One is evaporator, compressor, condenser, and the expansion or the throttle valve. The most widely used refrigeration cycle is the simple vapor compression refrigeration cycle. In an ideal vapor compression refrigeration cycle, the refrigerant enters the compressor as a saturated vapor and is cooled to the saturated liquid state in the condenser. It is then throttled to the evaporator pressure, and pressure vaporizes as it absorbs heat from the refrigerated space. The ideal vapor compression cycle consists of the four processes, that is ideal vapor compression refrigeration cycle. Process is 1 to 2, that is isentropic compression, 2 to 3, constant thermal heat rejection in the condenser, 3 to 4, throttling in an expansion valve, and 4 to 1, constant pressure heat addition in the evaporator. बस नहीं कुठे करते तिकडे करते So this is the pH diagram, is another convenient diagram that is often used to illustrate the refrigeration cycle. So look at the pressure enthalpy chart here, pH diagram. This you can see here the working cycle is shown, that is a evaporator, compressor, condenser, expansion valve. This is the cold refrigerator space, and this is the heat rejection to the warm environment. So pressure enthalpy chart diagram, which is oftenly used to illustrate the refrigeration cycle. So 1 to 2 is nothing but the compression which is being carried out in the compressor. Then 2 to 3 is nothing but the condensation, where the basically the vapors are getting converted into the from the saturation line, the liquid. And then in the 3 to 4, where there is a pressure drop of the liquid refrigerant, and then the liquid refrigerant it enters into the evaporator. In the evaporator again, the heat is extracted from the substance to be cooled or space to be cooled, and then again it goes to the second cycle, that is in the compressor. So in the temperature entropy diagram also you can see that if this is point 1, then this point 2 is being shown in the superheated region. This is the saturation line. So this point is nothing but the superheated line. And then again the condensation. Okay, if subcooling is there, then it will extend it in the left hand side direction. If there is no subcooling, then from this point 3 to 4 is nothing but the expansion. The ordinary household refrigerator is a good example of application of this cycle, which means that in the ordinary application, in the household application, we use the similar kind of basically the refrigerators. Okay, so let me check whether it is going on correctly or not. Yes. So the ordinary household refrigerator is a good example of the application of this cycle, because everywhere you will find the refrigerators which is being used at the household application. Okay. The result of first and second law analysis for a steady flow. Here you can see that the freezer compartment, then evaporator coils, then capillary tube, the kitchen air, condenser coils, compressor.
तो इंजन कुक जा रही थी ना
So results of first second law analysis for steady flow. So
मैंने
you can see that
तो
throttle valve delta is y
किया
greater
था
than 0. Evaporator P is equal to constant. QL is equal to M in bracket H1 minus H4. Then COP of refrigerator is equal to QL divided by W net in is equal to H1 minus H4 divided by H2 minus H1, because we have to go on to the earlier cycle, H1 minus H4, H2 minus H1. So this is the pressure enthalpy chart. So H1 minus H4 is the heat which is being absorbed, so refrigerating effect, and that is in the compressor work is being provided. That is nothing but the here H2 minus H1. So here we can see here the COP of the refrigerator is equal to QL divided by W net. So H1 minus H4 divided by H2 minus H1, and COP of the heat pump is basically QH divided by W net. So H2 minus H3 divided by H2 minus H1. Taking an example ahead for the refrigerant, one refrigerant we have considered. That refrigerant which we are considering now is nothing but the basically the 134A. 134A is the working fluid in an ideal compression refrigeration cycle. The refrigerant leaves the evaporator at minus 20 degrees centigrade and has a condenser pressure of zero point 0.9 megapascal. The mass flow rate is 3 kg per minute. Find the COP of the refrigerator, COP of the refrigerator with the Carnot cycle for the same. And T max and T minimum are the tons of refrigerant. So using the refrigerant 134 tables from the chart, basically we have taken these values like H1 is equal to 238.41 kilojoule per kg. Entropy also at this point we have taken 0.9456 kilojoule per kg Kelvin. Compressor exit also. Okay, and then the condenser exit also. So H3 is equal to 101.61 kilojoule per kg. And throttle exit T4 is equal to T1 is equal to minus 20 degree centigrade. H4 is equal to H3. So COP of a refrigerator is nothing but QL divided by W net in. Okay, so finally putting the values, we will get that COP of the refrigerator is 3.44. Okay, the tons of refrigeration often called the cooling load or refrigerating effect. Then QL is equal to M into H1 minus H1. So 3 kg per meter cube into 238.41 minus 101.61. So it is coming out to be 1.4194 ton. So COP of the refrigerator in the Carnot cycle, when it operates on the Carnot cycle, is TL divided by TH minus TL. So minus 20 plus 273 Kelvin divided by 43.79 minus of minus 20. So 3.97. कटिंगचं दुकान चालू राहते का बघा. Another measure of the effectiveness of the refrigeration cycle is how much input power to the compressor in horsepower is required for each turn of the cooling. So unit conversion is 4.715 HP per turn of cooling. So W net is divided by QL is equal to 4.715 divided by COP of the refrigerator. So it is coming out to be 1.37 HP per ton. So look at the actual vapor compression refrigeration cycle. In the actual vapor compression, the what we have studied till now is basically the theoretical vapor compression cycle. Now the practical or the actual vapor compression cycle, it will be differing, and you can see that this point superheated region here to subcooling and here. Okay. Then the heat pump systems. So heat pump operation and the heating mode. The basically in the heat pump you can see here in this particular cycle the outdoor coil is there, then reversing wall is there, then this is the indoor coil and compressor expansion valve, and here the reversing valve is there, and heat pump operation in the cooling mode. This is in the heating mode. Okay, this is in the heating mode. So in the heating mode, the fan outdoor coil, and here the color coding is also being given. This color code shows for a high pressure vapor. Okay, and black color code is shown for the high pressure liquid. Now the heat pump operation, cooling mode, outdoor coil, reversing valve. This is the indoor coil, fan, expansion valve, and the compressor. So these are the heat pump systems. Other kinds of the refrigeration cycle, that is a cascade refrigeration system. So let me take a review whether it is going on. Yes. Other refrigeration cycle, the cascade refrigeration system. Very low temperatures can be achieved by operating two or more compression vapor compression systems in series, which is called as the cascading. And the COP of the refrigeration system also increases as a result of cascading. So, what do you mean by the cascade refrigeration system? Here you can see that evaporator, compressor, then condenser, expansion valve, and here in the condenser, the heat is being rejected, and here the evaporator again, expansion valve, condenser, and again evaporator, which means that it is like a one cycle which is being shown in the upper part of the diagram, and this is the first cycle which is shown in the lower part of the diagram. Okay, so this is nothing but the here the evaporator and increasing the refrigeration capacity, because what is happen in the cascade refrigeration system, the basically the refrigeration capacity it is being increasing. Here H1 minus this point would have been there, but now H1 minus H4, which means that this additional refrigeration capacity which we are getting with the cascade refrigeration capacity system. Then multi-stage compression refrigeration system. So that is evaporator, then expansion valve, then flash chamber, expansion valve, condenser. You can see that here the high pressure condenser. Here it is a two stage, so multi-stage vapor compression system. So multi-stage means here what will happen? Low pressure here evaporator. Okay, expansion valve. Two expansion valves are there. Flash chamber is a high pressure compressor, condenser. Multi-purpose refrigeration system. A refrigerator with a single compressor can provide refrigeration at several temperatures by throttling the refrigerant in the different stages. So the expansion valve, this is the kitchen air. Basically, it is being which is being high temperature air, high temp because high temperature is there, and in the condenser, and refrigerant loses the heat and it delivers to the high temperature zone here. This is the refrigerator. Freezer is there, which is called as the multi-purpose refrigeration system. So refrigerator with a single compressor can provide refrigeration at several level by throttling the refrigerant in two stages. Like in our home also, we have the this type of where the additional refrigerator space is being provided, where the cold temperature can be achieved. Then liquefaction of the gases. Another way of improving the performance of a vapor compression system by using a multi-stage compression with regenerative cooling, and the vapor compression refrigeration cycle can also be used to liquefy gases after some modification. So here liquid removed, vapor accelerated regenerator, makeup gas, multi-stage heat exchanger like that. So gas refrigeration system, absorption refrigeration system. Okay, so only few part is remaining that I will continue. Okay. Then the power cycles can be used as a refrigeration cycle by simply reversing them. And of these, the reverse Breton cycle, which is also known as the gas refrigeration cycle, is used to cool the aircraft and to obtain the very low cryogenic temperature after it is liquefied with a regeneration. The work output of the turbine can be used. एक minute, just a minute. Huh? So power cycles can be used as a refrigeration cycle by simply reversing them. Reverse Brayton cycle, which is known as the gas refrigeration cycle. It is used to cool aircraft and to obtain very low cryogenic temperatures after it is modified with regeneration. The work output of the turbine can be used to reduce the work input requirements to the compressor. Thus, COP of a gas refrigeration cycle, it is given by QL divided by W net in is equal to QL divided by work of compression minus work of turbine out. So here you can see the gas refrigeration system, the turbine, compressor, heat exchanger. This part is nothing but the refrigerator. Then absorption refrigeration system. That is another form of refrigeration that becomes economically attractive when there is a source of inexpensive heat energy at a temperature of 100 degrees centigrade to 200 degrees centigrade. In absorption refrigerant where the refrigerant is absorbed by a transport medium and compressed in liquid form. The most widely used absorption refrigeration system is basically the ammonia water system, where ammonia serves as the refrigerant and the water as a transport medium. The work input to the pump is usually very small, and the COP of the absorption refrigeration system is defined as it is given as desired output divided by required input is equal to cooling effect divided by work input. So QL divided by Qgen plus WP. So this is the formula. Yeah, totally. Here in a absorption refrigeration system, even solar energy is being used. Solar energy is used, okay, in the generator. Expansion work absorbed. Thermoelectric refrigeration system. The refrigeration effect can also be achieved without using any moving part by simply passing a current through a closed circuit made up of two similar material. This is called as the Peltier effect. This is called as the Peltier effect. And the refrigerator that works on this principle is called as the thermoelectric refrigerator. So here the refrigerated space, warm equipment, cold plate, hot plate, it is being shown. So with this, we have completed the topic of the introduction to the refrigeration and air conditioning, and also the first topic which you have taken up today, that is also completed. So I will stop here, and we will continue in the next class. Okay, let me stop my presentation.
Okay, sir. Thank you.